Write an exponential model for each situation. Find each amount after the specified time. A population of 1,236,000 grows 1.3% per year for 10 years. First thing, we're going to set up this model. The model we're going to use is the A of t, or the amount after a specified time, equals p, the primary amount, times the quantity of 1 plus r, which represents the base of the exponential function, raised to the quantity of, and I did make it, instead of just t, bt, because this lowercase b in my exponent could represent a horizontal stretch or compression in case you come across a word problem that poses a situation such as the population doubles every 4 years. In that case, your b value would be 1 over b, representing a horizontal stretch of 4. The primary amount of people in the population was 1,236,000, so that represents P. 1.3% per year is our rate, and we have to change that rate from a percent to a decimal. So 1.3% as a decimal is 1.3 divided by 100, which is 0.013. And the specified time, which we want to find the population after, will be 10 years. We'll begin by plugging in each of these values. A of 10 equals 1,236,000 times the quantity of 1 plus 0.013 could just be 1.013 right away, raised to the 10th power. The first thing you'll do in your calculator is always combine the 1 and the rate as a decimal. You usually won't need a calculator to do the inside of your parentheses unless it's one of those problems where you needed to use 1 plus r over n to the nt. In that case, you probably need a calculator to divide r by n before you add that number to the 1. You're going to raise 1.013 to the 10th power. If you do that, you will get 1.1378747, and the list goes on. Do not round this number down to a shortened value of itself. Leave this entire number on your calculator screen. Then, right from there, multiply by your p-value of 1,236,000. After you do that, you should get 1,406,413.169, yada, yada, yada. Since we're talking about a population, we're going to round to the nearest whole number. You can't have part of a person. In 10 years, the population is about 1,406,413 people. Now we have a population of 752,000 decreasing by 1.4%. 1.4% as a decimal is 0.014. Decreasing implies that it should be negative. The time frame we're looking at this in is 18 years. We're going to use the same equation as before, and we're going to fill in the numbers just like we did last time. We have our initial value, 752,000, times the quantity of 1 minus 0.014. If you need to do this in a calculator, definitely do it. Way too many people make silly mistakes when I'm checking over work of my students. Now, I really should have filled in the actual time there, not t, since I wrote it as a of 18. That means everywhere I have t, I should have an 18. Since my base in this exponential function is a number less than 1, that means that I will be decreasing the initial value. I raised the 0.986 to the 18th power first. I got 0.77586, yada, yada, yada. I left that number on my calculator window, and then I multiplied it by the 752,000, which gave me, when rounded to the nearest whole number, 583,448 people. A new car that sells for $18,000 depreciates, so we'll have a negative rate again, 25% each year for 4 years. 25% as a decimal is 0.25. Because we're depreciating by that amount, we're going to make our rate a negative number. This will happen over a time period of 4 years. For a third time, we're going to use the same equation. A of t equals p times the quantity of 1 plus r. If we're adding a negative number, it will become a subtraction problem, raised to the t power. I'll fill in all of my values. A of 4 equals 18,000 times the quantity of 1 minus, or plus negative, 0.25 raised to the 4th power. The base of my exponential function will be 0.75. 0.75 raised to the 4th power will be 0.31640625. For a third time, I'll leave that number right on my calculator screen and immediately multiply it by 18,000. After doing that, I got a value of 5,695.3125. However, this is money we're talking about, so you need to round to 2 decimal places. When I'm looking at that hundredths place, it's the thousandths place value 2 that decides whether or not that 1 stays the same, or rounds up. In this case, it stays the same. Just quickly highlighting my first step of raising my base to a power. The parent function for each graph below is in the form y equals a, the vertical stretch, compression, or reflection, times b, in this case the base of the exponential function, raised to the x power. Write the parent function. That's one part of the instructions. Then write a function for the translation indicated. If it's a parent function, there is no shifting left or right. There's no shifting up or down. That means your horizontal asymptote is at the line y equals 0. The function is exactly 1 unit above the horizontal asymptote when x is 0. That 1 is actually my a value in the problem. B, or your base of an exponential function, is the number you continually multiply by. A lot of times when we have a picture of a graph, it's a little bit harder to figure out what number it is we're multiplying by. One thing you can do is make a small table of values on the side, comparing the x and y values. As x increases by 1, my y values are 1, 2, and 4. If I pay attention, I can see to get from 1 to 2, I needed to multiply by 2, and to get from 2 to 4, I needed to multiply by 2. My parent function will be y equals 1 times the quantity of 2 raised to the x power. Another way to figure this out, when the numbers aren't as easy to work with, is to divide any output value by the output value before it. 4 divided by 2 is 2. 2 divided by 1 is also 2. That right there means my base is 2. As for the translation of left 3 units and up 1 unit, my horizontal transformation can be found wherever the x is. In an exponential function, it's in my exponent, so x minus h in my exponent will become x plus 3. My k, or my up 1 unit, will be a plus 1, which will be found at the end of my equation. For this second example, I'm going to start right away with the table of values. I'm checking in at 0, 1, and 2. While I'm at it, I know that when x is 0, the y value of -4 is actually my a value. As I continue figuring out my output values, I can figure out my base. My base can be found by dividing any output value by the term before it, or dividing is also known as multiplying by a reciprocal. I could flip it around and try it that way. I could do my division as a fraction, or I could do my division side by side. Whatever way you look at it, we get b equals 1/2. So with my a value of -4 and my base value of 1/2, I get the parent function y equals -4 times the quantity of 1/2 to the x power. As for my translation, my right 2 units will be indicated by the x minus 2 in my exponent, and the up 3 units will be indicated by the plus 3 at the end of my equation. Find the amount for the given conditions. Principal value of $5,000, it's immediately going to be in the p-value. Annual interest rate of 6.9%. Moving my decimal twice or dividing by 100 gets me 0.069 as my decimal value. My time of 30 years means t equals 30. Compounded continuously tells me I'm going to use Euler's number e. The equation I'm looking to use for a continuously compounding interest problem is a of t equals p times e to the rt. Please don't forget order of operations. E is raised to the RT. First, we're going to multiply the rate times the time. We're going to get a numerical value. Then we will raise E to that numerical value. After we get that next answer, we will multiply that by P, the principal, and we will get our A, the amount of money at the end. Using the calculator, 0.069 times 30 is 2.07. Not every calculator has an E button, but E to the 2.07 power equals 7.924823. If I multiply that number by principal of 5,000, I'll get 39,624.115589 yada yada yada. Since it's money and we need to round to 2 decimal places, my final answer, the amount of money after 30 years will be $39,624.12. For the next example, I have a principal amount of money, which is $20,000. I have an annual interest rate of 3.75%. As a decimal, that is 0.0375. The time indicated by the problem is a 2-year window. The problem also tells us that our interest will be compounded quarterly. That means our interest rate of 3.75, while that is our annual interest rate, we will need to divide by 4, and that number is the amount of interest we'll get each quarter. This means we need to use the equation A of t equals p times the quantity of 1 plus r over n raised to the nt. The A, or amount, after 2 years is equal to 20,000 times the quantity of 1 plus 0.0375 over 4 raised to the 4 times 2. 4 times 2 is pretty easy. I'll just get 8 as my exponent. 0.0375 divided by 4 is probably the first thing I'm going to type into the calculator. It's actually super easy to just add 1 to it right away, so I'll do that in the same step. I'll have to raise that number to the 8th power. The calculator I'm using doesn't have the ability to use exponents. So on the side, I raised that number to the 8th power, and that gave me 1.07750076 ... When I multiply that amount, which is greater than 1, indicating growth, by 20,000, it gave me $21,550.15 after rounding. The amount after 2 years is $21,550.15. How long would it take to double your principal at an annual interest